we've already encountered an instance where we parameterized states, namely the state of a single qubit. We discussed that the state of a single qubit can be visualized as a point on the surface of the Bloch sphere, and that it can be parameterized by two angles corresponding to the angles that you use in spherical coordinates. So these two angles constitute a parameterization of a single qubit, a pure single qubit state. We can translate that also in the language of gates and circuits, because we can say that any single qubit state psi parameter with coordinates theta and phi on the Bloch sphere can be produced by a sequence of two gates, which I marked R, Y and R, Z. R stands for rotation. So each gate effects a unitary transformation, namely the unitary transformation which corresponds to a rotation on the Bloch sphere, in the first case around the y-axis, and in the second case around the z-axis. And the rotation about the y-axis is by an angle theta, and the rotation about the z-axis is by an angle phi. Yeah? So you see these parameters now again in the circuit, namely as parameters which specify the gates that prepare the state. Yeah? And you can prepare any single qubit state by a sequence of RY and RZ gates, just as I wrote it here, with varying values of the angles theta and phi. I would like to make a distinction here between the gate type and the parameter value that specifies the transformation effected by a gate. So looking at the first gate, the rotation about the y-axis by an angle theta. The gate type is a rotation about the y-axis. And this gate type is always the same, no matter which state you want to prepare. What varies is the angle, so it's by which you rotate about the y-axis. Yeah? And the same also for the second gate. Yeah, one also talks about parameterized gates, or parameter controlled gates. So the type is fixed, say rotation about the y-axis, rotation about the z-axis. This basic type is fixed, but the angle, so the parameter value, that varies from instance to instance. Now, moving on from single qubit states to multi-qubit states, we can generalize this idea. We can parameterize also many qubit states by some set of parameters theta. I denoted this on the right hand side in the ket with the vector symbol. So you have a whole array of parameters, theta I. And you can think of a circuit architecture where you have, which is fixed for any state that you want to prepare. So it's always the first step, say a single qubit gate, and the second step is a 2 qubit gate, and so on. And also not just the number of qubits involved, but also the type of transformation. Yeah? So it may again be that the first single qubit gate is always a rotation, say about the x-axis in this case. So the gate types and the basic architecture is fixed, but what varies from state to state are the specific parameter values. Yeah? So each gate is a unitary transformation, so some kind of rotation, and therefore the amount by which you rotate, that may vary from state to state. And this is the idea behind when one talks about parameterized states, and that's the idea behind some architecture, some circuit, yeah, which has a fixed basic structure but varying parameter values, which gives you a parameterized state. So after these preliminaries, I would like to show you one particular algorithm to find the ground state of an n-qubit Hamiltonian. It's not the only one. There are other algorithms, but it's one which I personally particularly like, I have to say, and which is also, I would say, rather close to being implementable with current day hardware, and also sort of relevant for practical problems. I think, as far as I know, at the moment, the classical calculations are still a little bit better than calculations done with the variational quantum eigensolver, but it's getting close, and this is a type of algorithm which has the promise and the potential of becoming actually practically useful in the coming years. In contrast to, for example, Shor's algorithm, which is a very famous algorithm because it can factorize large numbers, and if that succeeds, it would be able to break encryption protocols and so on. And for this reason, it's a very famous algorithm, but it's famous only on paper. It's still a long way off until Shor's algorithm can be implemented on actual hardware. But the variational quantum eigensolver has the potential of solving interesting problems in quantum chemistry and classical optimization problems, and it's a lot nearer in terms of practical implementation. And you will see that it has a design which is of a different flavor than the algorithms that we have seen before. Let me start with a setup, and it's just a symbolic representation of some setup that creates parameterized states, in the sense that we just discussed, that we have sort of a fixed basic topology, architecture of our circuit, and fixed gate types, but we can tune the parameters for each gate. This circuit creates parameterized states, and they are called, in this context, ansatz states. And these ansatz states, they are functions of the parameters, theta. For these ansatz states, we would like to measure the energy expectation value. So we are given the n-qubit Hamiltonian, whose ground state we are looking for. Yeah, and we are preparing ansatz states. They are parameterized, and we want to measure the energy expectation value in such an ansatz state. And this gives us the energy expectation value as a function of the parameter values. Yeah? And the measurement itself is done with a measurement setup using standard measurement devices, as in all our circuits, possibly with single qubit gates just before the measurement gate in order to rotate to the appropriate measurement basis. Yeah, so this is again a schematic drawing. In our example, we had Hadamard gates in some cases, but they could be other rotations in order to measure in the correct basis. So this combination of circuit which prepares ansatz states and then a measurement setup which determines the expectation values of various tensor products of Pauli operators. Yeah? This together allows us to determine the energy expectation value as a function of our parameters. And this is the quantum subroutine of our variational quantum eigensolver. So the variational quantum eigensolver is actually a so-called hybrid algorithm. So it's a mixed classical and quantum algorithm. And this is the quantum part. Around this quantum subroutine is a classical algorithm where we start with some initial set of parameter values, theta 0. That's the starting value. Then we do the quantum subroutine to determine the energy expectation value for this initial set of parameter values. I should also remind you that, of course, this quantum subroutine has to run several times for each set of parameters, because you have to repeat the measurements multiple times in order to get the expectation values. And then you embed this in a classical optimization algorithm. So you find the energy expectation values for your parameters, and then you shift the parameter values. You do the quantum subroutine again, determine the energy expectation value for this updated set of parameter values. And so basically you are moving around in parameter space of these thetas. And the classical optimizer tells you where to go in parameter space. And of course you want to go in a direction that keeps lowering the energy expectation value. And then hopefully after some time you arrive at a set of parameter values which are denoted by theta star, which minimizes the energy. And then the associated parameterized state, so the psi created with this choice of parameter values, that should be, well, we shouldn't expect this to be exactly the ground state, but it should reasonably well approximate the ground state. It turns out that this is a pretty efficient algorithm, and that the classical optimizer that in which you embed this quantum subroutine, that there are sort of good, efficient classical optimizers which, in combination with this quantum subroutine, allow you to find efficiently a good approximation to the ground state. And I should emphasize that it's not the exact ground state, unless you are lucky, but in general it's not the exact ground state, but it's just a good enough approximation to the ground state. Good enough in particular for example, the quantum chemistry calculations that you need. Now, what is the, without going too much into the specifics of this classical optimization procedure, what is the secret behind the efficiency of this quantum eigensolver? In principle, if you really wanted to find the exact ground state, then you would have to try out all possible states in your n-qubit Hilbert space. You would have to explore the full Hilbert space. And since the dimension of the n-qubit Hilbert space grows exponentially with the number of qubits, this would be not efficient. Yeah? The resources required would explode, would grow exponentially. The secret behind this success of this algorithm here is that in the circuit that creates the parameterized ansatz states, you embed typically 2 qubit gates, 2 or more qubit gates, but actually you can break this down into a sequence of 2 qubit gates, which create entanglement between the qubits. And so the circuit that creates the ansatz states creates highly entangled ansatz states, which are superpositions of many different basis states of your n qubits. And by producing these highly entangled ansatz states, you are effectively exploring multiple basis states of your n-qubit Hilbert space simultaneously. That's talking a bit loosely, yeah? But the idea is that through entanglement, you are, just as we saw in, say, the Deutsch-Joshua algorithm or the Simon's algorithm, where we created superposition states before sending queries to the oracle. Yeah, so we didn't send basis states through the oracle, but we sent superposition states through the oracle. Here the idea is to create entangled states, which are superpositions of multi-qubit basis states in the standard basis, and perform the energy measurement on these entangled states. And it turns out that then the number of parameters that you need, the number of thetas that you need in order to explore large parts of your n-qubit Hilbert space, this number of parameters does not have to scale exponentially with the number of qubits, but it's enough if it scales linearly with the number of qubits.